Hi everyone, this is still exercise 2, but now I'm going to solve it using the graphical method. I'm going to use most of this diagram as it is, but I'm going to use what's on that diagram to draw the graphical method. For the graphical method early on, we're going to make the statement that this situation is in equilibrium, the forces are in equilibrium, therefore the resultant should be 0. So the sum of all forces should be equal to 0. And we need to start with that. What that looks like, or could look like, is if at a force this way, an opposite force to the one we've got there, and an opposite force to the one we've got there, it starts and finishes at the same point, or it should be the same point. Okay, that's when the forces are 0. If the sum of the forces was not equal to 0, that's where we could have this situation. We could have a vector, add another vector, remember to add them head to tail, or tail to head. And if they ended up somewhere else, then when we went to check to see what the distance was from the start point to the end point, our resultant vector, this is not 0. But here, the start point and the end point are the same point, and I don't have a resultant vector. So we're going to use this. We're going to say that the forces here, forces are in equilibrium. So the sum of the forces is equal to 0. Okay. If we say that, we know that the tension in T1 and T2 must be sized so that it forms a closed shape. So what we can do here, I'll start with T1. Okay, so I'm going to start from a point and I'm going to draw on T1. And each point is going to be drawn from its own little set of axes. And because I've got X and Y in here, I'll continue with my X and Y. X and Y. Okay, my T1 is going to be here. And now, I need an arrowhead. From that, I'm going to add T2 or FW. It doesn't matter the order that you add them in. But I'm going to add T2 because it makes a prettier looking diagram for me. Okay, it from this point, can you see that it's 90 degrees? T2 doesn't go there. Okay, I'm going to draw this axis. Normally it'd be 30 degrees from my y-axis if my y-axis was here. So it's going to be 30 degrees in. Okay, that's still going to be 30 in there. And then, that's not going to close up. So I know, actually I'll start with my weight force down here. Be easier to draw it correctly. My weight force is down here because it was down 90 degrees from the x-axis. Down 90 degrees. And then my final vector is aptly sized, T2, at 30 degrees from the y-axis, so that the sum of the forces equals 0, so that it finishes at that point. And it needs to be drawn this way with arrowheads on there showing this, that it forms a closed shape, and therefore this is true. We know this was 90 degrees here, and that the angle in here is left with 60 degrees. Okay, this is quite a convenient shape because in this shape, let's see if I move it down from here. Okay. In this shape, we can just use basic trigonometry. You can use the cosine rule or the sine rule if that's what you know as what makes the graphical method itself. But we don't have to. For No, won't do that. The weight force we know was equal to 490.5 newtons. Actually, let's use the sine rule. We could use the cosine rule if we knew two sides and not the other one, and the angle of the side that we didn't know, but we don't know two sides, so we'll use the sine rule. Sine, I'll put the sides on the top. That means I have to label my triangle. A, lowercase a, capital B, lowercase b, capital C, lowercase c. It doesn't matter where you put A, B, and C, as long as the capitals are on the corners, the vertices, and the lowercase letters are opposite the angles that they represent. And in that case, we have, which one do I know? I know C. So C on sine of C is equal to a side I don't know. Let's say B on sine of B. Okay, multiply both sides by sine of B, so now I've got C sine B over sine C. These two are still multiplied together. There we go. Is equal to B. Fill in the values, which is 490.5 times by sine of 30 degrees over sine of sine C, which is 60, which gives us, the calculator says 490.5 times sine of 30 divided sine of 60, 283, 283.2 newtons. Okay, and this represents B. Sorry, I should have had that over here. B equals, okay, and B is the size of T1. So T1 equals B, which is 283.2 newtons. And then if we scroll down a bit, make a bit more room for the next calculation, we have, let's use the same thing as we did before, C over sine C, because that's what I know, is equal to, let's go with A over sine A. What we could do is rewrite this, and instead of A, we're going to say that that is T2. So, no, let's multiply both sides by sine A. So we get C. I'm gonna run out of room again. Need a longer page. Oh. We got moved in on. So C times sine of A over sine of C is equal to A, and my A represents T2 and my C represents FW. So I get 490 times sine of A was 90 degrees and over sine C, which from above here was 60 degrees, sine of 60 is equal to, not FW, is equal to T2. And when I work out this number as an answer, it should be, well, let's do it correctly. Let's set a good example. Okay. Our calculator says 490.5, I missed the 0.5, times sine of 90, and then divided by sine of 60. gives us 566. T2 equals 566.4. And we should see that answer is the same as our answer over here, and this answer is the same as our answer down here. Easy. And yeah, thank you very much.